Testing, testing, sound, sound. How do we? Is it good? Alrighty. Hello, good morning, everyone. Good afternoon, good evening, whatever this might find you in the world and in time. How is everyone doing here so far? I see we have a few people going connected. All right, this is exciting. Okay, let me regroup myself a little bit. Um, because what are we doing today? We're doing Christmas trees. Christmas trees. Yeah, wait. We're doing Christmas trees? It's the season to be jolly. Na 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 na. Na 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 na. Oh, and this is green. And it doesn't and it doesn't show up because of the green screen. All right. How's everyone doing? I think I've got, as usual, I've had a little too much coffee, and I also just got my booster shot this morning, so I'm a little like woozy woozy. Good morning, Andres. Good to see you. How's everyone doing? All righty. What are we doing today? Okay, so first things first. Hello, my name is Jose Luis, and I run this thing called Parametric Camp. We go live mostly every week, not always, unfortunately, but mostly. And we go live, and I get the chance to record tutorials on computational design. I do things such as Grasshopper, coding, C sharp, sometimes even Python. I have been known to do Python, even that, in crazy days. And then afterwards, after the recording, we do a nice polished tutorial, and we do series with that. So we were recording a hey Nicolas, we were recording a series called Advanced Development in Grasshopper, which we're still is still in the works, but we're taking a little break from that because we're working on this project about illuminating programmatically and with code the LED lights of a Christmas tree. And we've already recorded a couple videos on how to create a simulation for that. And then we recorded another video on how to create simple sequences that do not, that are just like random lights turning on and off, etc. But they do not really take into consideration the three-dimensionality of the tree or where the LEDs are placed in the Christmas tree. So we are going to do that today, this morning, in this video, in this recording. And hopefully what I would like to do is I do have the Christmas tree in my living room. So, but I am recording from a different room, so I need to figure out a way to throw a really long cable here from my room, from my recording studio, to the living room where the tree is, because I would like to make a video where I show all those sequences working and how I load them on the tree. So that's my wish for today. So this morning is probably going to be about how do we generate sequences for the tree that take into space the three-dimensionality of the tree. And then hopefully in the afternoon, I'll do another one, or in the evening, because I want to wait until the living room is dark so that we can appreciate the lighting of the tree as good as possible. Richard, Timothy, welcome. Good to see you. Alrighty. So what are we doing? What are we doing? How are we going to start? I have a few examples here, and the examples that I have. So this is where we were last week. So last time we recorded, we had the Christmas tree, and we could load, and we had the Christmas tree. We could load the coordinates of the Christmas tree from a CSV file. And then after that, we could recreate the Christmas tree like this. So we're using basically very small mesh spheres, and we're customizing the material that is used to display them. And then so we have the 3D Christmas tree. And if you're new to what we're doing here, the coordinates of this, of where the LEDs are coming from a calibration routine that my students and I were working on, and that is informed and inspired by this video, this YouTuber. Anyway, I will explain all of that in a second, but I'm not going to cover that in these videos. We're going to assume that somehow we have the coordinates. And once we have that, I have a video where we created the simulation, and I have another video where we created the rendering, and I have another video where we created simple sequences for this tree. The sequences that we did do not take into consideration the 3D coordinates. So those are just like, for example, things such as turning, what are these? Flushing the tree. Well, flushing the tree is the most boring one. Turning the colors on and off randomly, or turning them on and off randomly with color, or having them all pulse in and out. This is very slow, so I'm going to crank this up. Which one is this? The fourth one? 1, 2, 3, and 4. So let's say that the duration is 2 seconds and that the tree frame is 30 seconds. So we're going to, you see, pulsing on and off, on and off. All right. That's a little too much, I think. So we're going to keep 60 frames and 5 seconds duration. So that's going to turn on and off. And then, for example, what was this one? What did we do? This one was like all the lights blinking and turning on and off with a delay. That was nice, actually. That's actually really nice. I ran it on my tree and it looks really, really nice and really cozy. This one is also nice. It's the same. We randomly split all the lights into red and greens. This one is a little too much. My partner and I, we like more like delicate, minimalistic kind of designs for the Christmas tree. We tried this one. It was a little too bright, too red, too green, but you're welcome to judge when you see this sequence running later. And we have this one where it's basically, we're running through the numbers and we're turning a bunch of them on and off. This is going to be, in effect, it's going to look very similar to the one that I'm going to do first in this sequence, in this series. Now, so because what we're doing in this one is, if we have the 500 LEDs one after the other, we're basically turning on off a bunch of them based on their sequence, their position across the string. And because they happen to be very next to each other, it looks like a sequence. It's all right. So I'm making a mess here now. So I'm going to stop this, and I'm going to save this as sequences. No 3D. For example, and then I'm going to save another one that is going to be called sequences 3D, and that's the one that we're going to work with today. So I'm going to do this. All right. And hey, Mikael, good morning. So, all right. So then what we're going to do is we're going to develop some of these. So we're going to start the video, and for the video, I'm going to do, what are we going to do? So I'm going to do first, I'm going to design a sequence where we have a horizontal plane. We're going to imagine that horizontal plane is moving top to bottom or bottom to top, whatever, like vertically. And then we're going to turn on and off the lights based on where that LED, that plane is. Okay, so that's going to be one thing. Then we're going to do a similar thing, but with colors, with the colors of the rainbow. Okay, so that's going to be the second one. Then we're going to have like the rainbow colors move up and down on the tree. Then the third one is going to be The third one is going to be, we're going to color the trees, the LEDs, also with the colors of the rainbow, but circularly. So imagine a cylinder with all the rainbow colors like that. So we're going to do that, and then we're going to rotate it. That's also going to be cool. And then last but not least, I would like to do something where maybe we draw like a spline or like a path or something here, right? And then we have like, imagine like a light that was moving around, something like this, you know? And and then that light illuminates the tree, if you will. Something like that. I would like to try that out. So that's what we're going to do. So it's going to be 4 sequences. We're going to try that out here on the video. I hope to not make it very long. I have not been good at that. And then the next video in the afternoon will be just me running these sequences on the tree in somehow. I don't know how I'm going to do that yet. All right, so let's start first with the sequence of, and for that I'm going to go to the whiteboard. We're going to start with the sequence. So let's imagine, we're going to imagine we have the Christmas tree. I'm going to draw the Christmas tree. Are you ready for this? We have the Christmas tree. All right. I mean, that wasn't terrible. That was not terrible, right? Okay, and we're going to imagine that we have all the Christmas lights, and the Christmas lights are going to be somewhere in 3-dimensional space, somewhere like this. Okay, beautiful. So what we want to do first is we want to figure out the height of the tree. So what we're going to do is we're going to calculate. I don't like this pen. How about this one? Yes, this one. First of all, we're going to calculate the height. All right. We're going to calculate the height of the tree. And then after we calculate the height, what we will need to do is we will need to basically subdivide that height into a bunch of, oh, why is this not working now? Oh, it is working for you. Oh, I had this problem last time. Yeah, my screen for some reason just goes unresponsive. Let me reset this. I'm going to reset this. Let me first save this in case I lose it. Okay, so I'm going to, is there any way I can refresh this? Or something? Okay, well now it's working. Okay, so there, here, I'm going to subdivide it into a bunch of points. Then what I'm going to do is, for each one of those points, I'm going to imagine that there's a plane. Oh, this happened again. So wait, let me do. Nope. And you can see it, but I cannot. Why is this? Nope. What about if I do this? Nope. I still can see it. Okay, so I'm going to have to reset this. Okay, resetting that. Actually, it's kind of nice that you can't see the thing resetting. Okay. And I guess this is okay here, and this goes here, and this should be here. Okay, so I draw a plane over each one of these. And then what I do is I calculate the distance of each one of the lights to the plane, etc. And if that distance is within a particular threshold, then I turn that one on. Otherwise, I don't. Okay. Beautiful. So, so I think that's a good enough explanation to start. Okay. So I think that's a good enough explanation to start the video. I need to remember to do the introduction later, which I always forget. I'm actually going to write it down. I'm going to write it down. Record intro. Otherwise, I'm going to forget like I typically do. So I got it right there. Beautiful. Okay, are we ready for this, team? Is this happening? Woohoo! Okay, so let's do this. All right, let's get started. So, as usual, before we get into writing any code, it's good to think things through and to do like a couple of sketches about and plan out what are we going to be doing. Remember, the first sequence that I would like to do is a sequence where we're going to imagine we have a virtual plane, a horizontal plane that is navigating horizontally the tree in the z direction, either from bottom. Hello, hello. Wait a minute. Oh, now it's back? Yep. Okay. Well, that sucks. Yeah. Yeah, why did that happen? This microphone is not. I'm going to do something. Hold on, 1 second. So the microphone is Um, wait. Hello. Hello, 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 hello. Well, I guess we're going back to the old ways. um, okay, hello, hello, hi, yo, yo. All right. So I don't know what's going on with this microphone, but I don't want to figure that out now. So I'm going to be using the other one for today's stream, which still, I wonder if it still has the noise canceling. Let me double check something. Back microphone, properties, filters, noise reduction. Okay. What was going on? Hold on, 1 second. Yep. Okay. All right. So we're going to use the old one for today, and whatever. I'll figure out what's going on later. Okay. So I don't know. I don't know where we were, so I'm going to start from the beginning. Sorry for that. Okay. Starting over again. Beautiful. Let's get started. So I have drawn this amazing Christmas tree with these amazing LED lights that are all over the place because as usual, I would like to spend a little bit of time thinking ahead and planning with some sketching what we're going to be doing before we actually get into writing code right away. Okay, I think this is actually typically very good practice. So the first sequence that we're going to design is we're going to imagine there's going to be this virtual horizontal plane that is going to be traversing the tree from top to bottom. And then if the LED lights are very close to that plane, then we will turn them on or off. All right. So in order to do that, the first thing that we're going to have to do is we're going to have to figure out the height of the tree, if you will. We're going to have to figure out from all of those Christmas tree lights, we're going to have to figure out which one is the highest, has the highest Z value, and which one has the lowest Z value, so that we can move the plane between those two values. All right. So that's going to be one thing that's going to be easy to do with a for loop and figuring and reading all the coordinates first. And then once we have that, what we're going to do is we're going to subdivide that z space, so the minimum and the maximum, we're going to subdivide it into a bunch of intermediate steps. And how many is going to be equal to how many frames, so how many seconds do we have for the animation, the times how many frames per second we want to animate this. And this is going to be basically the position of each one of the horizontal trees in each one of the frames in the animation. And once we have that, it's going to be actually quite easy. What we're going to do is we're going to, for each one of the frames, we're going to make a calculation where we're going to imagine that we have a horizontal plane, and then we're going to calculate for each one of those planes, each one of those frames, we're going to calculate how far away each one of the Christmas tree lights is, and we're going to have some kind of value, like the width of the Christmas tree or something like that. We're going to calculate how far away each one of the LED lights are, and if each one of the LED lights falls within a boundary that might be defined by, for example, the width of that plane or something like that, then we will turn those lights on. But if it's not, then we will turn those lights off. And once we got this working, we will make it a little nicer. So instead of turning them on and off, we will work with like a gradient, etc., so that the animation is a bit smoother. Okay, I'll show you a couple tricks to polish this out. So that's going to be actually quite simple to do. So let's go back to writing some code for this. Okay, sound is great. Sound is working good, right? Is working good now? Thanks for letting me know, by the way, because otherwise I would have recorded the whole thing with no sound, which sucks. Okay. All right, so we're going to go back to... All right. Okay, so we're going to start. And what are we going to do for this one? Okay, so I'm going to copy and paste this. Flush, and then moving the plane. And then I'm going to add here a variable moving the plane. Okay, and then okay, and I'm going to turn that to 5, for example, and this is going to be the width. And then this is going to be of the type double, which you cannot see because it's going to my other screen. Okay, and then once we have that, we have the frame ID. I'm just looking at my notes here. Okay, how many LEDs do we have? The basis of the COC file, the length of the animation. So, okay, generate rows for each frame. So, okay, and then okay. Okay, I think I got this. Beautiful. So let's get started. I'm going to cut this. All right, let's do this. So I'm going to start with a simple file that is inherited from the work that we did in the previous video in this mini series, where first of all, we wrote a block here that was able to, given the coordinates of a Christmas tree, it was able to reproduce and create a list of points so that we could see them in three-dimensional space. So that was the first block, all right? So we have all the coordinates as points in three-dimensional space. And then we had another block where we could represent those points with small mesh spheres, because so that we could texture them with some transparency in the colors of the tree. And then we also wrote this other thing in the simulation video. This was actually 2 videos ago in the series, where given a CSV with the coordinates of all the points, and given a CSV with the RGB colors for each one of the frames in the animation, we could render and we could animate that sequence here using this simulation and this special rendering. And then on top of that, in the previous video, we generated a set of sequences, right? A set of sequences that were working with the location along the line of the LED lights. So their position in the string of lights, but they were not working with the 3D coordinates. This is what we're doing in this video. So as a template, I just kept the very, very first sequence that I called flush. And I called it flush because it was basically a sequence where all the LEDs just turned black, which is very useful when you just want to, basically, when you have the tree and you want to turn it off, as I will show later in more videos, all right? So I took this sequence and I copy pasted it, and I added so this is the same one, right? I just changed the output, the name of the output, and I'm calling it moving Z plane. And to the flush sequence, this is the exact same one. I added this new parameter called the width of the type double, all right? Which is going to be how far away the LED has to be from the moving horizontal plane so that we turn it on and off, all right? And I'm going to input here some kind of slider. So for example, I'm going to call that's going to be 1, but it's actually, because the tree is actually very small, I'm going to crank this down a lot, all right? And that's going to be, it's going to be 0.1, for example, okay? And then we are here, all right? And we can start writing code for this. So remember, the baseline, the template that I have right now is if you remember from the previous video, we basically start the CSV file by creating a row that has the header, which is the ID of the frame and the RGB colors for each one of the LED lights, right? And then what we do is we calculate how many frames the animation has, which is basically the duration of the frame in seconds times how many frames per second do we want to render this animation at. And then for each frame, that's basically how many frames we have calculated, we have this for loop that for each frame generates a row. That's going to be each one of these rows in the CSV file that starts with the ID of the frame and then 3 numbers, which are the RGB colors for each one of the LEDs. Correct? Beautiful. So here for this one, basically the RGBs are always going to be black. That was the flushing template that we have from the previous example. So what I would like to do now is I would like to add code here so that first of all, as we said in the diagram, the first thing that I would like to do is I would like to calculate the extremes of where is the lowest LED light and which one is the highest. In order to do that, we're going to do that before we actually get into, I'm going to write here pre-calculations before calculations for I'm going to call it pre-calculations for the whole sequence. All right. So what are we going to do here? The first thing is calculate minimum and maximum Z of all LED lights. All right. How are we going to do that? I'm going to define 2 variables called minimum Z and maximum Z. All right. I'm going to start them. All right. And then what I'm going to do is I'm going to write a for loop where I'm going to iterate over all the LED lights. So I'm going to go int I equals 0, I is less than LED count, which is a variable that I calculated before, and I plus plus. All right. And then what I would need to do is I would need to say here if the coordinates of this LED, so that's going to be if the coordinates of so LEDs is a list of points. If LEDs I, so that's going to be the LED that I'm checking right now. If the Z coordinate is greater than maximum Z, it means that it is higher than any of the maximum Z's that we have set before. So what we're going to do is we're going to set that value, maximum Z, to that coordinate. All right? What we're basically saying is we're basically starting with some values for minimum, maximum, and then we want to say if we found an LED light that has a coordinate that is greater than whatever we found before, then set it to that value. Otherwise, if LEDs I dot C is smaller than any coordinate that we have found before, then store that coordinate into LEDs into minimum Z. All right? Now, we need to remember that because we're using these variables to keep track of the minimum value that we have found so far, right now we're not initializing them to anything. We could say, well, maybe I can initialize them to 0, but if I initialize them to 0, then, for example, if all the tree is on the positive end, then we're basically not going to, if all the trees in the positive end, then 0 is always going to be the minimum because all the coordinates of all the points are going to be somewhere in the positive range. So what we need to do is we need to actually initialize these values to either a very large value or a very small value. So for example, for minimum C, what we want to start, it was like with a really, really large value so that all the coordinates starts giving us less values. So we could start with like some random, really large number, but typically a good way of doing this, is using the maximum value that is possible for a double number. And we can find that by using double dot, and then from the double object, you can see that there's a property called max value, which is whatever the maximum value a double number can take. If we start with this number, then we know for sure that all the LEDs are going to be somewhere under this. And therefore, as soon as we start finding coordinates that are less than this maximum value, we will start updating the minimum value for this. All right? This is a very simple search. And similarly for max, we want to start with the minimum value possible for a double value, which will be a very negative number. All right? So just to make sure that this is working, let's print out, for example, minimum value dot toString. All right, and let's also print the maximum value. All right, of this. I'm going to put here a panel, and we can see that the minimum value is 0 and that the maximum value is 2.14 or something. The fact that it's 0 actually makes sense because when we wrote the code for the calibration, we snapped and we forced all the coordinates to start at 0 and to end somewhere in however high the tree was. So this actually makes a lot of sense. It's not a coincidence, all right? It's part of how we wrote the other code for the calibration of the tree, all right? Beautiful. Therefore, we can also find the height of the tree. So that's going to be very easy to do. So, for example, tree height is going to be equal to maximum Z minus minimum Z. All right? Beautiful. Then what are we going to do next? Okay, what we're going to do next is we're going to calculate the uh, the step size. Okay, all right, yes. Just like we have calculated the height of the tree, we're also going to calculate how far away these points are in between them. And that's going to be very easy. It's going to be just as simple as saying, I'm going to calculate the step in the z direction, right? And that's going to be equal to how high the tree is divided by how many frames we're going to have in the animation, all right? So that's going to be it. And actually, just before I forget, it's actually not going to be exactly how many frames we have, but it's going to be how many frames we have minus 1. Because remember, if I have something and I divide it in, and I have 3 frames, then what I need to divide that whole thing is in 2 parts, because the divisions is 1 times less than the amount of points that I want to have across that length. All right. So if my tree only had like 1, 2, and 3 frames, I need to divide the whole distance by 2 so that I can calculate the distance between those 3 points. All right. All right. So now I have the height, I have the step. So I think I'm ready here to start writing the algorithm that for each frame calculates where the plane is and the distance to each one of the LEDs. In the diagram that we used to explain this, we were talking about a horizontal plane. So we might be tempted to actually use a plane object inside of Grasshopper. But if you think about this, because this scenario is very simple, it's just basically a horizontal plane. The horizontal plane is always going to have the same z height. So we don't actually need to work with a actual plane so long as we know the z height of each one of these points that we're calculating for each one of the frames. We can basically just use that value, that z value, and calculate and subtract from the coordinates, the z coordinate of each one of the points, to find the distance between this virtual plane and each one of the LED light points. If we were working with an inclined plane or something like that, maybe using an actual plane will make things easier, but because we're going to be working with a straight horizontal plane, then just working with the z values right away will make things actually easier. So for example, for each one of the frames, all right, here what I'm going to do is I'm going to calculate the height, the z height of the virtual plane. That z height is going to be, let's imagine that the plane is going to move from the bottom to the top. So what we can say is the z height is going to be equal to the minimum height, so where the lowest light is, that's going to be minimum z, plus how many frames we have navigated so far, 1 frame, 2 frame, 3 frames, 4 frames, times the step between those frames, which we calculated before, right? So that's going to be equal to f, which is the frame that we are at, so 0, 1, 2, 3, 4 times the step in the z direction that we have calculated before. So how far away we are, how far away in z each frame is, all right? That's going to be the z for this frame. That's the z, or I'm going to call this frame z or plane z or something like that, all right? Beautiful. Then for each one of the LEDs, we already have a for loop that is going over all the LEDs. For each one of the LEDs, we can here calculate, first of all, I'm going to calculate the z, I'm going to calculate the distance of this LED to the virtual plane. So what I'm going to do basically is I'm going to calculate the difference in z is going to be equal to, excuse me, is going to be equal to, the coordinates of, so these LEDs dot so the z coordinate of this plane, of this point, or sorry, of the LED that I'm checking, minus that z value that I just calculated before. So that's going to be plane z. All right. And then what we can do is we can say if dz is greater than the value, if it's smaller than the value of the width, then the coordinates of RGB, all of these should be 255, 255, and 255. All right. However, otherwise, this should be 0. And I think that can be it, except for one minor thing that I'm going to discuss in a second. All right. So let's see if this works off the bat right away. All right. So I'm going to press play, and it looks like we have no errors. And so let me then plug in the CSV here into the simulation. All right. I'm going to plug it in here. I'm going to reset, and I'm going to press play. All right. So we can see that something is happening. We are moving up, and as we're moving up, it looks like the tree is lighting up, but it's lighting up fully. Okay, and then it looks like it resets. It reset again, so the whole thing is lighting up. There's no turning off here, so something is happening, but we definitely need to put some more work on this. So what is going on? Well, first of all, the one second. Is this correct? Mm-hmm. Okay. Mm-hmm. One problem that we're having, and the reason why this whole tree gets illuminated, is that because we're moving up, we can see that the coordinates of the C, as we subtract the coordinate of the plane, this value can be positive if the LED light is above the plane, but it can be negative if the LED light is below the plane. And because we're comparing whether if that difference, that distance, is less than the width, it turns out that when it's negative, it's still less than the width. So what we would need to do is, in order to avoid all the lights turning on, I mean, this could be fine if you just want the tree to just light up and down, but since we want the whole plane to, we want that effect of a block of lights turning on and off, what we need to do here is we need to work with the absolute value. And we need to say if the absolute value of that distance is less than the width, then you need to turn on. Otherwise, you need to turn off. All right? So let's see if this works now. So I'm going to reset, and I'm going to turn the whole thing again. And voila! We have something now that is working a little better. All right? So we now have this effect of the tree moving up, and I think we can just crank up the width. You know, you can make it wider, or we can make it, all right, not so, so for example, 0.5, all right, which is a lot. So you can see maybe this is a little too much. We're going to do 3.5, okay? And we can see that there's like this virtual plane that is somehow kind of in the center right now. and it's moving up, etc., and it hits the top, you know, and it jumps to the bottom, which is kind of okay. All right, so it's good. Now, this animation is okay, but to me it's not great because we're working with the lights being on or off. And I think it would be nicer if we have some kind of gradient where the lights that are farther away are dimmer and the ones that are closer to the plane are brighter. All right? How can we implement that? Okay. Okay, so let me draw something here. Hey, Daniel, Chandra, Arasto, welcome. How are you doing? Okay, so can I draw it here? And we imagine that we have the Christmas tree somewhere here. All right, and we imagine that this is the distance. Okay. And then I think, okay, so okay. The way we're going to do this is very simple. So let's imagine I'm zooming in here, for example. Let's imagine I'm zooming in here. And the way I'm going to do, we have the situation like this. We have the plane, we have the LED light that is somewhere there. We have the distance that we have calculated to this virtual plane. And we know that the maximum, the width, is somewhere here. So this LED light is turning on because it's within that range of the width. So the only thing that we need to do is we need to figure out for this distance how close in relation to the maximum width that LED light, how close it is to the actual plane. So for example, if it's somewhere, here, it feels like this is more or less 0.6 times the width, the maximum width, or something like that. Or if it was here, it would be like 0.1 times the width. And if it was here, it would be like 1 times the width. What that means is that we need to find proportionally how far off it is within that width. And then, using that proportion, figure out a value between 0 and 255 that corresponds to how bright this would be here or how dim it would be here. So 0 for this point and 255 for a point that would be super, super close. So we just have to map a number within those two ranges, okay? So what is that going to look like? Well, let me stop the animation first. Let me stop the animation. The way we're going to do that is we're going to say, first of all, we're going to calculate the z. And we're going to say if we are within range, then what I'm going to do here is I'm going to calculate something that I'm going to call the brightness, all right? And I'm going to calculate this, the brightness. And the brightness is basically going to be is going to be that distance, the distance that we calculated. So that's going to be the absolute value of the z, all right, divided by the width, okay? So that will give me a value between 0 and 1, all right? However, for this one, if I do this, so that's going to be a value between 0 and 1. If I do that, then values that are very close are going to give me values that are close to 0, and values that are very far from the plane are going to give me values that are close to 1. So what I need to do is I need to invert that by saying 1 minus that value. All right. If I do that, then values that are close to the width will give me 0, and values that are close to the plane will give me ones. Will give me values of 1. All right. And then the only thing that I need to do is to multiply this whole thing. This whole thing is, which is something that goes between 0 and 1, multiplied by 255. Well, 255. All right. And so that's going to be the value of the brightness. But remember that lights need to have an integer value. So what I need to do is I need to make sure that this value is actually an integer. And what I can do is I can cast that value using the integer cast here. All right. And then once I have that, then that value of the brightness is the value that I can set for each one of the RGBs. If the LED is not within this boundary, then I still keep it at 0. All right. So let's see if this works. So I'm going to, I have an error here. There is no explicit conversion between double to integer. Are you missing a cast? All right, so how can we fix this? How can I not cast? Oh yeah, am I doing, is this the problem? Yes. Yeah, the problem is that I deleted what I should not have deleted. That's my intuition was telling me. So if I write this casting like this, it turns out that only the first part of the expression gets casted because casting gets precedence. So, and then this part remains a double, and that's why it could not be stored here. So, well, basically the only thing I need to do is I need to wrap the whole thing in parentheses to make sure that this casting is happening to the whole expression. As I do this, then this now works, and I believe like, oh, we're already seeing something here. Let me turn this on. So now you can see that as I turn, whoa, how cool is this, right? So you can see now the plane, and you can see the gradient of lights that are going and are moving through the plane. How cool is this, right? If you were confused by when I did the 1 minus, all right? When I did 1 minus here, we can see what would happen if I didn't do that. So we would have the exact opposite effect. You can see that the lights that are closer to the plane are the darkest ones because this value is close to 0, and the ones that are farther away have the value of 1. Okay? So 1 minus will flip this situation and will give me, I can reset this now, or not. What is going on here? Okay, so what did I do? 1 minus blah, blah, blah. Ah, no, sorry. The 1 minus was here. 1 minus, that was the problem. Okay. All right, beautiful. Now, one last thing, one last very small detail is going to be the fact that I like to generate animations that can loop infinitely in a smooth way. And you can see that this plane, as it approaches the tip, you can see that the animation jumps to half of so some of the LED lights turn on at the base. That is because technically what's happening is that when the plane reaches the top LED, the animation ends and we go back to the beginning. And because of how we have designed the animation, the plane being in the bottom means that all these lights are turned on, and the plane being at the very top means that all the lights at a width distance below it are also turned on. That doesn't create a nice, smooth animation. So what can we do about this? Well, we're going to do an actually very simple trick, which is that we're going to imagine that the tree is actually larger on the bottom and larger on the top. And how much larger and how much smaller? Well, something that is going to be equal to the width. Why that? Because what we want is the very first plane to start at a point where the light that is the closest, it's still at a distance that is going to be turned off. But at the first frame, the very first frame afterwards, this light will start getting color. And similarly, for the last plane, we want the last plane to be as far away enough so that the last LED, the one that is highest, also gets turned off. So the way we're going to do this is very simply, we're just going to hack a little bit the calculation that we did, and we're going to say whatever the minimum value that you calculated and the maximum value, let's just increase those by width so that we can loop the whole animation smoothly. Increase these values by width to ensure a smooth looping animation. All right, so what we're going to do is minimum C is going to be decreased by the value of width, and maximum C is going to be increased by the value of width. That's it. The rest is going to be the same because now the virtual height of the tree is going to be a little larger, but then the step is also going to be a little larger, but everything is going to adapt accordingly. If you see, did you see what happened? We started from pure black and now it's moving, blah, 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 and it's going to keep going, and the plane will also end up somewhere virtually above, but above enough so that the topmost LED fully turns off. And you can see that now it happens here. It also turns on. Ta-da! Awesome. We have now created an animation where the plane is moving up and down, but the full thing loops smoothly and nicely. And I'm actually going to show you this later on the tree, and it looks actually pretty good. All right. So this was the first animation, the one that is a moving plane across the Christmas tree, taking into consideration where each one of the LED lights are in the three-dimensional space. As I said before, this was a very simple version where the Z is the horizontal plane. The plane is purely horizontal, so we could work directly with the Z heights. But this example could be very easily extended to have an inclined plane, and then to calculate the linear projection, linear distance of each one of the LED lights to that plane, and use the same technique that we have used before for the value of that distance. All right, it's just a little bit more code calculating the planes of the distance, but I would be very happy to leave that option to you, the viewer, to try it out on your own. If you do it and you want to share with us in the comments or in Discord, I'll be more than happy to share that as well. All right, let's go on to the next sequence. All right, folks, how are we liking this? Isn't this very freaking cool? Just wait until you see it running on the tree. It's going to be really cool. All right. Okay, so what is next? The next thing is we said okay. We said the same thing, but what we need to do now is we need to calculate we want like a rainbow kind of animation. All right. So we want a rainbow that is moving up and down in the Z height. Okay, so how are we going to do that? How are we going to do that, and how am I going to explain that? How am I going to explain that? Let me stop this and let me go back to the drawing board. We kind of made a mess here. I'm just going to save this. I'm going to save as a. Okay. And I'm going to perhaps remove this layer. Okay. Do I want to delete this layer? No. I may also need to explain a little bit about HSV colors. Herpes simplex virus, no. And then HSV to RGB in C sharp, because I used no, I used this one. Yes, I used this one, copy link. I'm going to paste it here. And I'm going to, okay, and okay, so we got that. So this works. And HSV color. How can I explain HSV color? Okay, and then my diagram is going to be that in this case we don't have this, but what we want is okay. Okay, I got it. The next sequence we're going to design is going to be super similar to the previous one. It's also going to be a horizontal plane that it gets animated, if you will. But what I would like to do in this one is I would like to have all the lights animated. I would like to have all the lights always light with a particular color. But what I would like to do is, as we move up the tree, what I would like to have is some kind of rainbow of colors that gets animated over frames. The idea is that rainbows of colors can be done pretty easily using a color space that is not the typical one we use, RGB, but it's a color space that is called hue, saturation, and value. And what's nice about this color space is that if we want colors that are not primary, so orange, yellow, purple, pink, that kind of stuff, if we want those colors, we don't have to figure out the weird RGB combination, because what's inherent about the HSV color space is that colors are defined by hue. And hue is typically a value that goes from 0 to 360. And depending on which value we set, then we can move smoothly between those colors. So if we set a value of the color for example, 45, we get yellow. But if we start increasing by 1, you can see how we transition from yellow to green to blue to a darker blue, etc. So working with one number that goes from 0 to 360, we can change and we can oscillate between different colors of the rainbow, creating a very nice effect, a very nice visual colorful effect, and just by setting values from 0 to 360. Okay. Now we will eventually have to convert from HSV to RGB, but let's put that a little bit to the side for the moment. So the challenge here then is to figure out over time which color from 0 to 360 each one of the LEDs is going to have. And then the way we can do this is very easy. So we can use conceptually is the similar technique that we used before. We're going to divide time into a sequence of frames. So we're going to say how much time do we have, how many frames do we have, and then what we're going to do is that for each LED, what we're going to do is that we're going to start that LED value in the first frame to a value that corresponds from 0 at the very bottom to 360 at the top, and so that at the first frame the color is somewhere in that rainbow spectrum, and then every frame we're going to increment that value. So for example, for this maybe starts at 160. For every frame, we're going to increase that 160 by how many frames we have navigated times the amount of steps in the hue spectrum that we have, given how many frames we have. All right. So that's going to be equal to a value that we're going to call, for example, a step in the hue or something like that, right? It's very similar to this idea of a moving plane. We just don't have a plane anywhere. It's more about having an LED light that starts with a value of hue, but then that value of hue gets increased over time based on the frame that we're at. Okay, and then once we calculate that value of the hue, we will be able to translate that into RGB colors and then set that value for each one of the LED lights. So the way we're going to do that is we're going to start first by making sure that we have the full rainbow, no static, no animation, just one rainbow, okay? And then after that, we will just write code to start moving it over time, okay? Let's take a look at how we would do that. Okay, so I have copied the example that we did before, the moving zipplane. I copy pasted it here. I changed the name. Now it's called Moving Z Rainbow. And I also removed the width input because we're not going to be using that anymore. All right. And now, of course, I have some errors because the code is still relying on width, whatever. So I would like to now make some modifications here together with you, so that we can adapt the previous example to this idea of the animation. So, for example, for the pre-calculations, I still want to calculate how many frames I'm going to be working with, duration times frames per second. I also want to pre-calculate the minimum height and the maximum height of the tree. But in this time, because we don't have the idea of the width, we're not going to need to increase it or decrease it by the width. Okay, so that's also not going to be a problem. The tree height, we still have this here. The step in the C height, this one is also not going to be the same anymore, because now for us the height is not what's important as we navigate. What we're going to need to do is we need to now change and say we need to create a new value that I'm going to call the step in hue, which means that every time, every frame, what I will need to do is I need to increase the hue value. Actually, let's put a pin on this one because we're not going to need this one yet for the first example where I just want the rainbow, no moving anything, okay? We're not going to need the Z height at all as well. But what I would like to need is I would need to calculate for each one of the LEDs, all right? I would need to calculate, I will need to, let me remove all of this, okay? Let's start from scratch. For each one of the LEDs, based on how high it is, I'm going to need to calculate its hue value, all right? So I'm going to say hue is going to be a value that is going to go somewhere from 0 to 360. But it's going to depend on where the tree, I'm going to start, I'm thinking the very first frame. For the lowest point, it's going to be a value that is going to be super small. For the highest point, it's going to be, so for the lowest LED is going to be a point that is going to be close to 0. For the highest point, it's going to be close to 360. So what I need to do is I need to figure out where that LED is within the minimum and the maximum, right? And then multiply that by 360, basically. So that's going to be saying, where is my Z height? What is the Z height of this LED? So that's going to be let's I dot Z divided by the tree height. What is this tree height? The tree height, all right? But I need to remember that I need to subtract the minimum of this distance. Because if the tree happened to be somewhere up, the height, the location of this needs to be subtracted by the minimum so that we have the relative location of the C point along the height of the tree, right? So this is going to give me a value that is going to be somewhere, it's going to give me a value that is going to be somewhere between 0 and 1. And then what I need to do is I need to multiply this by 360, all right? And then after I have that, I can say, well, R should then be the value of hue, green should be the value of hue, and blue should be the value of hue. This is not going to work, obviously, but this would be more or less, okay? So what errors are we getting here? Well, we can convert from double to integer. So let's do the casting where we cast all of this to an integer, and then hue is also an integer, all right? And as we do that, then you can see that we have constant, all the LEDs have the same value, right, across the simulation, and this is probably going to give me some error when I plug this in because RGB values cannot be greater than 255, correct? 258 is not a valid alpha, etc., etc. Yes, all right. So what do we need to do now? We have a value of the hue, all right? So that means in the color spectrum, where are we? In the color spectrum, it tells us where we are in this color hue spectrum. But it turns out that the way LEDs work is that they need RGB colors. Turns out that the HSV space is typically defined by H, hue, being a value from 0 to 360, and then the saturation and the value being values that go from 0 to 100. And that's how you define also darker colors, lighter colors, etc., etc. There are ways to convert from RGB space, and you can see in this diagram, you see saturation from 0 to 360 and value from 0 to 1. There are ways of converting HSV to RGB colors. We're not going to get into that in this video. Maybe I can make a video at some point about that. So what I'm going to do is I'm just going to go to Stack Overflow and then just copy and paste literally these two functions that someone has created to convert from color, regular RGB to HSV and vice versa, okay? And what I'm going to do is I'm going to copy those. I'm going to paste them here. I like being knowledgeable about crediting people for their work. So I'm going to also copy the link here and make sure that in my code, I write, hey, this is coming from this link here. And then also this function, I also took it from there to give credit to the author. all right? And then what you can see is that here, what I have is a function that given a hue, a saturation, and a value, they will return a color that will have those RGB values embedded in them. So what I can do here is I can now say color, if you don't remember, is an object that is not coming from Grasshopper, it's coming from the C# standard libraries, but I need to explicitly import it here. So I need to say, I need to use system.drawing, which is the namespace that contains the object color, all right? And now I can generate here I'm going to call this hue color, and that's going to be equal to this function convert color from HSV with a value of hue that I just calculated, and then saturation is going to be 100, and then that value is going to be, I think this might work in the 1 and 1 range. Am I correct? Saturation, yeah, 1 minus saturation, 1, yes. So this is not going from 0 to 100, it's going from 0 to 1, all right? And once I have this, I can now say from this color, I want the red value. And from this color, I want the green value. And from this color, I want the blue value. All right? Are we ready for this? Are we ready for this? Woohoo! Nadan! So it works, surprisingly. It works. You can see that we start at red, which I believe is where the color space starts. Yes, it starts with reddish, and then as we go up, it turns orange and blue and yellow. So as we go up, orange, yellow, green, blue, purple, magenta, blah, 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 and it circles back to red. Okay? It's just that now we can't really animate this because we haven't actually worked with the values. The same values, the same RGBs stay throughout the whole animation. So what we need to do now is we need to, and just something to make sure that we understand what's going on. If we take a look at this, and if I were to change this value now to 180, for example, you could see that what happens is that the full tree, in a sense, is wider. You can see that we only get a spectrum of 180 across the tree, and there's all these colors that are missing. If we were to, instead of 360, if we were to double it to 720, probably what will happen is that we get 2 times the spectrum of the rainbow. So we get like half the tree is one full rainbow and another half tree is another full rainbow. And we can multiply this by 3 and we get like, how much is 360 by 3? I believe it's 180 like this. Or something. That's probably not the exact number. Maybe it's 10. Yeah, maybe it's 10. Yeah, it's red. So now we have 3. So we could work with how many times we want to iterate over the full spectrum. Okay. But now what we want to do is we also want to be aware of where we are in simulation time. So each frame, what we would like to do is we would like to make sure that the color changes over the frames. And the way to do that is just going to be as simple as for every LED, every frame that goes by, we're going to increase the hue color by a tiny bit. And that tiny bit is going to be how many frames we have in the simulation divided by the full spectrum, in this case, 360. So that's what I was starting to do here when I said, well, instead of the step in the height, what we want to calculate is the step in the hue. And that's going to be equal to how many frames do we have divided by, no, actually the other way around. 360 divided by how many frames do we have, all right? Now, that's going to be frame count. I would like to raise a word of caution here, and it is, remember that C# by default does integer division because frame count is an integer, and because this value is also an integer, right? It turns out that this division will be an integer even though we're storing it in a double. So I need to make sure that I cast one of the 2 values to a double to make sure that the division has integer precision. double precision. So I can do that very easily by taking 360 and just adding dot zero to make sure that the computer takes it as a double number. And the only thing that we need to do here now is once we calculate the initial value that is here, the only thing that I need to do is I need to say, make sure that I add to that value an amount equal to how many frames have elapsed, f, times the step in the hue value. All right. So I'm going to do that. And then I think we can now run the simulation. I'm going to reset it and we can run it and you can see how it's slowly moving down. See the red color? Can I speed this up somehow? Can I speed this up? Yeah, 3 seconds. You can see the color navigating and you can see they're moving down. This is actually really cool in the tree. Let me do it even faster if we can. Can we do 1 second? Can we do 1 second? Let me reset this. Woohoo! Very trippy. All right. Just to make sure that we understand, if I had not done this, we would have, the same. Okay, so that's surprising. But anyway, just make sure you keep that always in mind, just in case. I'm sure that if we don't do this, we have some kind of precision error or something like that. All right. Beautiful. So we have a tree with a rainbow moving vertically from the top to the bottom. How awesome is that, right? What is the next animation that we're going to do? All right, for this one, the next one that we're going to do is one that I haven't tried yet. So I'm actually going to try it right now. So what we're going to do for this one is that the tree is going to be, we're going to do for this one is that we're going to create the same animation, but it's going to be a radial animation. A radial animation, yes. Okay. All right, and let me try that out real quick so that moving radial rainbow, and for that radial rainbow. So let me try it real quick and then I will explain that in the tutorial. So for this one, same thing. We really don't need this. Really, in this case, we're going to assume that it's in 0, 0. So we're going to calculate, and the step in the hue is equal to frame count 360 times frame count. Calculate the R. So for each one, I basically need to calculate the angle. The angle is going to be equal to a new. I'm going to design. How are we going to do this? Let me do this real quick. So we have the x coordinate of the LED. That's going to be the x coordinate. The y coordinate is going to be LEDs dot y, and then the angle is probably going to be math.a10 to y and x, and that's going to be between 0 and 2 pi, correct or not? What does C# math A10 to, what is the range of values? the angle measured between minus pi and pi radians. Okay, that's fine. That works for us. The angle, and that would need to be multiplied by 360 and divided by math.pi to turn it into degrees. And if we okay, the angle, and then what we can do here is we can say int hue is going to be equal to int of angle multiplied by 360 and divided by hue. And then we're going to do that. So, and if we do that and I plug that in here, we had an error, and the error is that minimum, blah, blah, blah. We have this error here. And where is minimum and maximum? Hue from blah, blah, blah. And then 84. What is 84? Oh, yeah, we don't need the tree height either. We don't need the tree height. And whoop. Up on the top. Is this working? It's not really working. So why is this not working? That doesn't make a lot of sense. Where is 0, 0, by the way? Wait, the tree, they're not centered. Oh boy, that's not cool. That is not cool. Oh no, that's a problem. I thought the coordinates were roughly centered. So can we bring a point as the center? Okay, so can we bring a point center, and that's going to be of the type point 3D. Where are you? Here. And that can be a point that we bring in. So that's that point. We bring it in. Okay. And then we basically say minus center dot x minus center dot x. If I do that, or it's the other way around. It's center dot x minus the coordinates of this one, I think. Oh no, I was doing the y. Sorry. Center dot y minus the coordinates of this one. And it's the other way around. Minus the center at x, and then center y minus the center y. Yes, exactly. And but this is weird. It's only working like in this, not in that direction. That doesn't sound right. Oh, it's not changing because I haven't really written any animation here, right? Because this should be plus F first step in the hue. Something's off. Hmm. Something is very off. That's weird. I wonder what's going on. Okay. Step hue, frame count. Well, let's forget about this, because this is also not working well in the first place. I've been looking at this for so long that it's starting to blink and rotate, and it's starting to like, I feel like I'm high or something. Okay. Um, I wonder if the problem is with if f equals 0, print u.toString. It's going from, okay, so in the first place, this should be 180. Hello. All right, we're back. Thank you, Gustavo. Thanks for that. So if I were to now print, okay. So if instead of that, I were to print the value of hue, what we would get is a value of from minus 178 to 179. I wonder if the problem is that the hue value cannot take negative values, and that's what's messing up in the conversion algorithm, perhaps. So let me crank this up by 180. If we up this by 180, then all those values go from 1, and then we get the full spectrum. So I guess it's just a matter of the conversion algorithm that is just not working. Oh. So I guess that's going to be it. Okay. So that should be it. And because then this is going to be equal to plus f times step hue, right? And that should give me the radial. Choo-hoo! All right. This is kind of cool. All righty. Okay, lessons that we have learned. It's very good to practice before you do anything. That's one thing. Second thing is when you copy paste code from out there, you got to be careful. Okay, that's another thing. I'm going to, yes. So, okay, so I'm going to copy and paste this somewhere else here so that I can, okay, and then I can just start the code again. All right, so we got this working. We got the tree. So now how am I going to explain this? So we're going to go to the drawing board. Oh, wait. It's going to, okay. I'm going to save this one and I'm going to save a new one where I don't have all this stuff. No, I can actually keep all this stuff. It doesn't matter. I can turn it off just right here. Okay. And then in the next one, so okay, so I'm going to draw the tree here. Okay. I'm going to draw a few Christmas lights. So that's going to be this one, and that's going to be this one. All right. And then what I'm going to do is I'm going to explain this by saying, well, we have a center. What we need to calculate is two things for each one of the Christmas tree lights. We need to calculate, first of all, for each one of them, we need to calculate. Oopsies. We need to calculate, for example, the angle and then we also will need to calculate, and we're going to use this for the value. We need to calculate, I haven't tried that, but actually I should have tried. We need to calculate that distance. I'm going to call the radius. Mm-hmm. Um, Okay. All right. So let's give it a try then. Okay, let's do it. Beautiful. Next sequence that we're going to do is going to be very, very similar to the previous one. We're going to play also with an animated rainbow. But this time, instead of animating the colors in the Z direction, what we're actually going to do is that we're going to animate the colors in the, how can I call this? Like along a vertical axis in an angular way around the tree. So what we're going to do is we're going to imagine that the tree is center at a particular point, right? And then what we're going to do is for each one of the LED lights, we're going to calculate the angle that is forming with the x-axis, for example, or with some kind of axis, and we're going to use that angle as the value for the hue, so that as we move in the full rotation of the tree, all the LEDs are going to be somewhere in the rainbow spectrum from 0 to 360. That's going to be one thing. And maybe, I have to think about this, maybe we also want to calculate how far away that LED light is from the center, so that maybe we can design a rule where the farther away it is, the brightest, and then the LED lights that are closer to the center are dimmer, maybe. I don't know. We can actually take a look at that, or not. I don't know. I don't know yet. So let's see what that would look like written in code. All right. All right, great. Okay. So I went ahead and I took the code that we wrote before, the moving rainbow in the Z axis, and I copy pasted it, right? I changed the name here to moving rotating rainbow, etc. And I added a new parameter, which I'm going to be calling the center, and that is going to be of the type point. Because if I look from the top perspective of the tree, what I would like to know is I would like to define, for example, a center as a point here that I'm going to load into, did this work? So set one point, I'm going to load this point, and now it's here, okay? I'm going to use this point for the calculations of where the LED lights are in relation to that virtual center, okay? I am not using, in this case, I'm not calculating parametrically the center by looking at all the coordinates and calculating the average, whatever, because since I have these outliers here, the actual center geometrically of all these points would be somewhere here, and it's probably not so for this particular one, I'm actually going to hard code this value with a point, okay? So, and I'm going to stick to the top view for this one because it's going to make things a bit easier. So what we're going to do is we're now going to modify the code that we wrote for the previous one, the one in Z, so that we first are able to statically create colors for the tree that change in the rainbow depending on where they are rotationally around the center of the tree. Okay, so how is that going to look like? Well, first of all, if I go to the previous code, I can probably imagine that right away I don't need to do any pre-calculations of the height of the tree. I don't care about this anymore. So that's going to go and that's going to go. And as I do that, I get all these errors because I'm using minim, all the variables that I deleted, I'm using them somewhere. But I can fix that later, okay? I still need the total length of the animation, so how many frames, all right? And I also still need the same, so how much each one of the LEDs is going to increase in the hue color every frame. And that's going to be 360, which is the total possible, divided by how many frames do we have. And now here for each LED, I'm going to totally ditch this. I'm going to write it from scratch, okay? The first thing that we're going to do is we need to calculate for each LED, we need to calculate the angle that that LED has with the, let's call it the x-axis, for example. The way we can do that is, first of all, we need to calculate for each LED, we need to calculate the difference between where, we need to calculate how far off in the x and the y directions this LED is from the center. That can be done very easily by saying, can I calculate the difference in the x direction is going to be where this LED is in x minus the x coordinate of the center point that I imported. And similarly, I can do that for y, all right? And then I get those two values. Beautiful. Once I have those two values, I can calculate the angle using this built-in function in C# called the A10-2, all right, which is different than A10. A10, the simple A10 is the arc tangent of an angle. So that's one thing. That's an arc tangent of an angle. But here, given two numbers, it was the tangent of the angle between those two numbers, all right? So this is typically referred to as the x and y coordinates of a point. And also a word of caution, it's very important to notice that because A10 and A10-2 are very similar, typically the notation is that the first value you want to input in A10-2 is the y coordinate, which is a little unintuitive, and the second value you want to input is the x coordinate, all right? Another important thing to notice about the A10-2 function is that the result is always going to be in the range of minus pi radians, so minus 180, to plus to positive pi radians, or positive 180. This is also kind of unintuitive because other functions we may have worked with may give us results in the range of 0 to 360, okay? So it's something to keep in mind. So how does that work? I'm going to calculate the angle, and the angle is going to be the math.a10-2 function of x and y, all right? Beautiful. Just for the sake of making sure that I know where I am, I'm going to stop all of this, okay? And I can't really do that, I think. So, sorry, never mind. So now what I would like to do is I have this angle, which I have calculated it, and the result is given me in radians. So what I want to do is I want to convert that to degrees, so that I get a nice value between minus 180 and positive 180. And I can literally just use that right away as the hue value here. So I'm going to calculate hue, and I'm going to say the value of hue is going to be converting angle to degrees. And we can do that by multiplying it by 180, right? And then dividing my math.pi, all right? And remember that I need to cast this to an integer, so I'm going to integrate all of that. And once I have that, then hue gets picked up, gets converted, and then I use that for the RGB colors. Let's see what's going on here. If I do that, I get an error, and X and Y, what is X and Y? Why is it not there? Oh, because it's dx and dy. So that's a flop on my end. So I'm going to run that, and it looks that it's working, but I need to plug this into the visualization. So let's plug this into the visualization and plug this in here, and I'm getting something. All right. Now, one word of caution, I'm getting something which is kind of what I expected. I have my point here, and it looks like for 0 degrees, it starts in red, and it starts in the positive, starts going orange, yellow, green, etc., which we already saw. That is kind of the natural direction for 0 and positive, all right? The problem that we're seeing here is that the other half, the negative half, is actually not working at all. It's giving me weird values for some reason. In researching this example, I actually found out that the reason for that is that the functions that we copy-pasted from the internet to convert from HSV to RGB do not account for hue having a negative value. And when it's a negative value, then things get messed up. So we could either fix this function, which would be nice as a contribution, but something else that we can do is, because we know that the range of values that we get from the angle is between minus 180 and 180, if what we do is we just add 180 to whatever value we get from the angle, the result will be that all the values go from 0 to 360. Let me show you that. So if I print here the value of hue to the console, right? What I'm going to get is, you can see that I'm going to get values that go from blah, 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 whatever. And if I use a domain bounds, and I plug it in here, you can see that what this gives me is the domain that includes all the values that I'm getting out of there. You can see that I'm getting values from minus 179 to plus 179. If I just offset all those values by 180, then you're going to see the result is that all the values are now going from 0 to 359. And it turns out that that was the problem that what we were having here, but now as we do that, the full tree is now covering the full hue spectrum. So it was just a problem with this function, it just couldn't take negative values, all right? So we're basically artificially offsetting this by 180. We could also offset it by 360 if we just wanted to make sure that we start with the red value in the x coordinate, okay? So that's fine. Beautiful, so that's up to us. Now, it looks like this is giving me a sequence where all the colors of the tree, all the colors of the lights are radial and it's working well. It's just that it's static. Right now, if I animate this is not moving at all, right? So very simple. The only thing that we need to do, as we did in the previous example, is that now that we know the base color for the hue, right? What we want to do is every frame, we want to make sure that that hue color gets increased by an amount which is equal to the amount of frames that have elapsed by times the tiny increase in hue value that every frame should have, which we calculated here as the step hue. So this is going to be as easy as when we calculate the hue value, just make sure that we add an amount that equals to how many frames have elapsed. So that's f, the iterator in the for loop, times the step in the hue spectrum. And if I do this, ta-da! How cool is this, right? Let's see this in 3D. Now we have the color, the RGB colors, which are now rotating. And if we had a solid tree, we would actually, because we would not be able to see through, we would actually be seeing these colors rotating very nicely. All right. We will see that in the example that we're going to do later on. All right. Now, something we could do is we could implement, as I said, we could implement this length here so that the values that are closer to the center have a shorter value, and then the colors, because of the value scale, the colors would get darker and would eventually tend to disappear. That's actually very easy to do, but we would now then have to take into consideration the fact that the tree is not really a cylinder, it's more like a cone. So the points here on the top, because they're actually very close to the center, will be darker than the ones in the bottom. So it's kind of a little bit of a mess. So it will take a little bit more of calculation. So I'm actually going to, this video is getting too long already. So I'm actually going to leave that up to you, the user, the viewer of this video, to figure it out. And I'm going to go in and figure out the last sequence that I want to do in this video. Okay? Which one is going to be? Okay, and before we do that, I'm going to try it out so that I don't run into problems like I did before. So let's try it out. I'm going to stop this. I'm going to stop this. I'm going to copy and paste this. We don't need a center now. Oops, oopsies. What is it gonna moving, rotating when it's gonna be moving spotlight or something like that. Moving spotlight. All right. Moving spotlight. Beautiful. I know. Sorry. So I'm going to be a path, and this is going to be a curve. So basically, what I'm going to try now is to create like a path of sorts. Let me. I'm going to create like a curve in 3D, and I'm going to use that curve as the trajectory that some kind of moving circle, moving light would be doing. We're going to imagine that there's like a moving circle, a moving sphere that is moving around that curve, and that it's illuminating the tree. Okay. So how are we going to do that? Let me flash the tree because I'm very distracted by it right now. All right, so that's going to be the new sequence here. I'm going to do the path and then the radius, which is going to be a number. Okay. Frame count. And then all of this needs to go. And then I'm going to start with R equals 0, green equals 0, and blue equals 0. Okay, so I can get the tree. Beautiful. And now let me draw some kind of curve that is going to be like this, like this, like this, and then it's going to spiral back down and close it up. And then I'm going to modify the control points. I'm going to move this curve a little bit up in 3D. Okay. And I want, okay, so this one, what do I want? I already want this one to be at the very top. And then this one needs to go down. Okay, and this one. I should have drawn this in 3D in a better way. This is just not very nice. I have no idea. This is very difficult to see. What if I change this to a layer that is like red or something? No, what have I done? Sorry for... Okay. Okay, so I have this, and 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 I have this. This is a very confusing. Okay, so I feel like, okay, so I feel like I'm messing this up. So I want something a bit smoother. So I'm going to bring this a little down, and this a little up, and this a little up, and this a little up, and this one far higher up, and this one is going to be the top. Oopsies. And this one is going to be the top. Yeah, how about that? Maybe I want this closer. That sucks. That is a terrible... Oh boy. That is a terrible... Okay, but let's imagine... So let's imagine we have this curve that we're bringing in. Imagine this curve, and then we subdivide multiplication. We multiply this by this, and we divide the curve in this amount of points, and we have a sphere of radius whatever. And the radius is going to be whatever here, and we're going to cherry pick from 0 to 2, let's say 300. Okay, let's say 300, and then let's say 300 here, list item here, here, and then that's the boundary, and then if that's the maximum, then we can just go what? Okay. All right, or something like that. Okay. You probably want a bigger radius. Okay. So then as we do that, what I want to use this as a way of illuminating the tree, basically, that kind of trajectory. So what we can do is that the path can be this one. I'm basically trying things out right now. So frame count is going to be whatever, and then we need to divide the curve, path divide by count, and that's going to give me the segment count is going to be frame count, include ends through point, and then I need and then point 3D BTS. I have that, so that's working. And then I want to print here frame count, and I want to print here pts.length.toString to make sure that they are the same. Because I'm not sure if by doubling the points we get different values. No, that's actually kind of good. Beautiful. So if I do that, then what we can say is point 3D and PT is going to be equal to points dot f, and then for each LED count we can calculate the distance. Double D is equal to let's I dot distance to PT, and if D is smaller than the radius, then int brightness equals 0. If it, then brightness equals 255. And then here we can just say this has to be equal to the value of brightness. And if I do that, whoa, something's happening. Something is happening. Okay, I'm going to turn this off and I'm going to run the simulation. Ooh. All right, so it looks like it's working. So maybe if I push this inside a little. Okay. And what I probably want to do now as well is to make it so that it's not just a hard edge, but is kind of, it's relative to the distance. So what I want probably to do is brightness is going to be equal to a value that is going to be equal to, well, the distance divided by the radius. So 1 minus that times 0.25. So that's one, so int, and then that, and then that, and then that. How does that sound? Whoa, much nicer. All right. Okay, so this is working. So we're going to do that. And I'm going to just cut this and paste it somewhere here. And my sound is still working. Okay, and it's 12:20. I have to go very soon. All right, so how are we going to do this? Well, we're going to start with the diagram as we typically do. We're going to start with a diagram. We're going to start with a new diagram. And then in the new diagram, we're going to say, well, we're going to have some kind of trajectory. All right. We're going to have some kind of trajectory. We're going to imagine that there is a kind of object that is rotating. I'm actually going to use a different color. All right, so we're going to imagine there is some kind of trajectory going on. So that's one thing. And then we're going to imagine that there is an object traveling that. So what we need to do is basically say from the center of that object, we calculate distances, right? And if that is within that distance, then we illuminate it. And if it's not, then we do a gradient. That should be easy to explain then. And the last sequence that I would like to do in this video is going to be actually super simple. It's going to be a bit more geometrical and a little less mathematical than the previous ones, if you will. What we're going to do is that we're going to imagine that there is some kind of trajectory, and this trajectory is going to be literally a curve in three-dimensional space wrapping the tree or whatever. And what we want to do is we're going to imagine that we have this object that is kind of, we have this object here that is kind of traveling through this trajectory in three-dimensional space. We're going to imagine that the object is kind of a sphere of sorts, for example. And what we would like to do is we would like every frame, we would like to calculate if the LEDs are somewhere in the range within that sphere. And then if they are contained inside of that sphere, then the LEDs should turn on, otherwise they should turn off. The effect that this will create is the effect of a moving object that is illuminating the tree, and that is a kind of a cyclical animation. Yep, I think that's pretty much it. Things to consider is that the way this is going to be is that we're going to have to draw that path in 3D space. We're going to have to subdivide that path in a bunch of points, and those points are going to be as many as the frames that we have in our animation. And then for each one of those frames, we will calculate if the LEDs are close enough to that center to turn them on or off. And then maybe we will all turn them off, full brightness or not, or we will do some kind of gradient between them. Okay, so let's go back to coding. All right. Moving spotlight, and then moving spotlight. All right, and then no center. We need a path here, and we need a radius. The path is going to be a curve. The path is going to be a curve. What are the curves here? And then the radius is going to be a double. I'm going to remove this here, and then I'm going to bring in a curve. That's going to be this one path. Whoops, we already have this path here. I'm actually going to bring this whole animation thing in that I did here, because why not? Okay, so we have this. All right, beautiful. Can we flush the tree to see it? Okay. Alrighty. Okay. As usual, the way we're going to start is we're going to copy and paste the last sequence that we did, the moving, rotating rainbow. I just copy pasted the whole thing straight here. And then what I did was I removed the center input, and I created two new inputs. One is going to be a path, and that path is this curve, this 3D curve that I've created wrapping the tree, kind of creating this virtual sort of path around the tree, and then a radius that is going to be just a number. And I don't know why my tree is gone. Yes, so you can see how the path is kind of wrapping the tree, and I have also a radius defining how big that virtual sphere is going to be. I have taken the liberty to just play a little bit here with a kind of animation of what this might look like. The path that I have here is going to be subdivided in many points, as many as the frames that I have in my animation. And then I'm going to have this virtual object as a circle here. This object is going to be virtually moving in this simulation over the path. And then what we're going to do every time is just calculate whether if the LEDs are within this sphere, and we're going to then calculate the value of the illumination based on that. All right. Now, this was all just pure visual flavor to explain the concept, but we don't really need any of this. So I'm just going to remove it from here. Okay. And we're going to go into the code, and we're going to modify the previous example to see if it works, to adapt it to the new situation. All right. So what do we do? First of all, we still need to calculate the total length of the animation, but now we're not going to be working with hue. So what I need to do is I don't need to calculate the step. What I need to calculate though is all these points that are going to be the intermediate points along the path that are going to be considered the centers of the animation of this virtual sphere. All right. So the way we're going to do that is that we're going to take the path, which is the input curve, and we're going to divide it by count. If you see the overloads, you can see that it's asking me for the number of segments. So that's going to be frame count, whether if I want to include the ends or not, because I will want to include them to have a perfectly seamless animation, right? And then the overloads gives me the points. So the return type of the function is going to be the parameters at which those points are found along the curve. But there's an overload that gives me also the points already for those parameters. So what I'm going to do is I'm going to say, yes, I want the points, and I want them in a variable called PTS, which I haven't defined yet. And I'm going to define that variable as an array of points through this, because that's what the overload was telling me. So this becomes an array that contains all the points that are each point for each frame. And then what I'm going to do here is I'm going to remove all of this. Okay. And then what I'm going to do is, first of all, I'm going to say for every frame and every LED, what I will need to do is I need to calculate for this LED so first of all, for each frame, I need to figure out which is the center that I'm going to be using. So I can fetch that from the array by saying the center point is going to be equal to, from the array of points that I calculated before, the one that corresponds to this frame. So that's going to be F, all right? And then here, what I can do is, for that center, I can calculate the distance to the LED that I'm currently calculating illumination for. That distance D can be, for example, I can say center, I could use Pythagoras, or I can use center dot distance to the LEDs in position I, which is the one that I'm currently taking a look at. And then I can say, I can do the following. I'm going to define, this is a bit more of an elegant way of doing this. I'm going to define a value called brightness that I'm going to initialize at 0. And if nothing happens, that value, brightness, is what's going to go for the R, G, and B values. All right? However, here in the middle, what I want to do is I want to write something where I say, if the distance happens to be less than the radius, so that value that we have as an input, then I would like to change the value of brightness, which I initialized to 0. In this case, let me just start by setting it to 255. Okay, so it's full bright. And let's see if this works. It looks like it works. We don't have an error. So I'm going to plug this into the simulation. So plugging it right here and right here. And oh, it looks like something is working. So it looks like the sphere is moving here. And now it's moving over here. And now it's moving over here. Can you see this? Choo-hoo! So this is looking great. So I have the animation almost working. This point is a little too far away, so I'm going to bring it over here. Oh, that's even worse. But it looks like like this is working. And if I increase the radius, probably we will have a larger effect. So you can see that more points now get illuminated, okay? Which kind of sounds reasonable. But of course, you know me already, this idea of like on and off, it's kind of not nice. So can we work with an animation where the color, the illumination of the LED is a function of how far away it is from the center? Yes, we can. It's actually quite easy. It's very similar to what we've done before. So what we can do is we can say, well, instead of a hard-coded brightness, let me calculate a value of the brightness that takes into consideration the distance. So first of all, let's calculate the relation between the distance and the radius. Okay, so that is going to be d divided by radius, which means that if d is equal to radius, if we are at the boundary of the sphere, then the value of the brightness would be 1. If d was super close to the center, then the value of the brightness would be 0. Okay? However, we want it the other way around. We want values that are close to the boundary, we want them to be 0, and close to the center, we want them to be 1. So we do 1 minus this value. But also, we want values that are not between 0 and 1. We want values that are between 0 and 255. So we're going to multiply this whole thing by 255. And because we need an integer, and these ones are doubles, we're going to cast this whole thing to an integer. All right. And are you ready for this? What? Beautiful. Check this out. How smooth and nice this animation is. Now we don't have lights that are turning on and off like la la la. It's just a really smooth and sleek animation of this. Let me crank up the value of the radius. We want like a little bit more. All right. It's very nice, huh? I don't know if that, yes, that is very nice. And if we saw this in 3D, we could really see how it looks like it's moving. So we're gonna see that when I run these examples in the tree. All right. Beautiful. With this, I think this is all I wanted to do for this video. We've actually done 4 sequences, 4 very interesting sequences. I'm very happy about those. Vertical plane, moving up and down. Same concept, but with rainbow lights rotating around the tree. And this idea of a sphere that kind of moves, this spotlight that is kind of moving around the tree. Okay, I thought this was a lot of fun and super interesting geometrically as well. Now, the way I would like to wrap this mini series is that I would like to take all the sequences that we've done in the previous videos and this one, and I would like to run those by the tree. So if you're excited about seeing how this looks like in the real world, maybe you want to check the next video in this sequence. There, a card or some kind of something will pop up at some point here, pointing you to that video. And in the meantime, if you found this video interesting, useful, entertaining, fun, or curious, whatever that is, maybe you want to show some gratitude, liking the video, subscribing to the channel, leaving a comment, or whatever that looks like for you. Okay? And remember that I'm recording this at the end of November 2021. And if you create your own sequences, I will be happy to take them and run them on the actual tree in the community, in the Parametric Comp community meetup that we do every year close to the Christmas holiday. All right. So I will probably just like connect the webcam to the tree and show them. But you'll see more of that if you're subscribed to the channel. You'll see notifications and all of that. Okay. Thank you very much and hope to see you on the next videos. Bye bye. All right, and I have to record the introduction and then we're done. All right. Okay, let's do this. Hello, this is Jose Luis here at Parametric Camp, and welcome to another video in this mini series of Christmas tree illuminations and the holiday seasons. Blah blah blah. Hello, hello. It's the season to be jolly. Na 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 na. Okay, you didn't come here to hear me sing. So, what are we doing in this video? This video is a continuation of the previous ones in the mini series where we were working with a Christmas tree that has a string of LED lights attached to it, and we were creating computational illuminations for those LED lights. All right. In the previous videos, we have done simple animations that only took into consideration where those LED lights were along the strip of the 500 LEDs. But in this one, I would like to make sequences and design animations that are actually aware of the XYZ location of those LED lights on top of the Christmas tree. So what we've done is we've created sequences like, for example, where we had a horizontal plane that was moving from the bottom to the top of the tree. And there was also a gradient between which lights were turning on and off. We did a very similar concept, but instead of using a white plane that moves and turns them on and off, illuminating the full tree with a rainbow of colors that was also oscillating in the vertical direction, and another sequence that did a very similar concept, but where the colors were oscillating in around the tree radially. All right. And last but not least, we also designed this one animation where we created this virtual path. Literally, we drew a curve in three-dimensional space around the tree. And then we imagined that there was a virtual sphere that was traveling through that curve. And as the virtual spotlight is traveling through that curve, illuminates certain areas and center lights of the tree. All right. All of this is because we had the possibility of running a calibration routine to figure out where the trees, where the LEDs are, where the LEDs are in three-dimensional space, and that routine was inspired by a video from YouTuber Matt Parker, a video that he did last year, and where he wrote some computer vision. So all of the work that we did is very inspired by his work. Thanks a lot, Matt. That was very awesome. And that calibration routine and all of the work in the background was also done by some of my students here at the university. So I want to thank all of those for their contributions. Thanks a lot. So in this video, I'm going to show you how to create those animations that are spatially aware of the tree and their position of the LED lights. And hopefully, by the end, the last video in this mini series will be showing you in an actual tree with an actual LED lights, how all these sequences that we've done in the mini series, how they look like. All right. So if you're excited about this, I invite you to join to watch this video. What am I saying? I don't even know what I'm saying anymore. All right, let's get hands-on. Let's start. All right, that was a lot. Okay, I think I'm done for today. Oh, yeah, and I have a faculty meeting actually. Oh, okay. I have to go because I have a meeting at the university. Thank you very much, everyone. I will probably stream this evening at some point as soon as I figure out how to connect to my webcam to the tree, and I'll run all this by the tree, etc., etc. Thanks a lot. It was very fun. See you on the next one. Bye bye.